So we implemented this query in 3 different pattern languages, and the fact that we could do so suggests that there's something in common between them all. And in fact, there is. What it is the relational algebra. And this is one reason why I've been trying to hit this throughout this quarter, is that, you know, if you put your relational algebra goggles on, the whole world starts to look like relational algebra. And you can start to see that these languages are not really all that different, and you can kind of look past the details of the syntax and see that what's actually going on is a relational algebra expression. So in this particular case, that expression might look like this. And I say might because this is not necessarily a rigorous statement here on the slide. So there's 2 joins, as we saw, 3 instances of the relation R, and this symbol means a select condition, where we're selecting for the predicate P equals regulates, and here the predicate P equals associated with, and here the predicate P equals interferes with. So now we have just the tuples that have the predicate with interferes with, just the tuples that have the predicate equal to regulates, and just the tuples that have the predicate associated with. And then we just do the join, where the object of this one equals the subject of this one, and the object of this one equals the subject of this one. All right. And so this, you know, if you look back on the earlier lectures, we talked about relational algebra. I hope you can convince yourself that this will produce an equivalent result. Now, as we said with the relational algebra, this is actually a specification of the order in which the operations should apply, while the other languages was more of a declarative expression of what the result should be, but not necessarily how to get the result. And that's generally the difference between the algebra and these languages. One of the benefits these languages give is they try to put aside any specification of exactly how it should be implemented and just specify the conditions that must be true of the result. And that's what we mean by declarative languages. All right. So fine. Maybe all 3 of these languages are equivalent, but I'd argue they're not. There's a benefit to the SQL implementation and the data log implementation, which I'll try to motivate by rewriting the query in a slightly different way. So imagine now, instead of having one big table called triples or called R with all the edges in the graph, imagine you had 3 different tables that came perhaps from different sources or different databases that you would combine together into one database. And each one of these tables represented different parts of the original graph. So you had an drug interaction database that had a relation interferes with, and just with 2 columns in it, you know, where the semantics of each tuple was the drug in the first column interferes with the drug in the second column. And from a completely different database, you had a facts about what drugs regulate which genes. Perhaps this is mined from the scientific literature. Perhaps this is derived from one of these public databases where some of this information is tracked, and so on. And then third, you might have a different database associated with or recording what genes are associated with which diseases. And so this is a very likely scenario, I claim, and in fact, again, this is derived from an actual example we have from working with our collaborators, and it's very much true that these different kinds of relationships came from different sources. And so it's actually more likely for you to have them in this form than it is for you to have them as one big graph. You actually have to do some pre-processing to merge them in together as one graph. But until you do that merging, you can't use that Sparkle language. And in fact, you can't use any graph language, and you can't really use any graph database. Right? They only work on graphs. And so while it's a very general data model for capturing arbitrary relationships, it's not clear that the world is always represented as graphs in its source representation. It's represented as a bunch of tables that happen to have graph edges encoded in them. And so being able to work with them in the original format is a strength. And you can do so in, say, data log. So here, the query actually gets a little bit simpler. You have a join between these 3 separate relations, and you no longer have to sort of query on, specify the predicate that defines each one. Okay, and that's perfectly fine. If you have a mix of graphs and relations, you can handle both with data log. And in fact, you can process them the same way as you would any other query with the relational algebra, with your implementation of the relational algebra. Similarly, in SQL, SQL has no problem with expressing this query if the data was represented in this form. You would do a join between these 3 tables, and you just have the join conditions, and the query actually gets a little bit simpler. So I guess what I want to bring home is that graphs tend to not appear in the wild isolated, right? They're not sort of free ions. They tend to be uh, applications tend to be hybrid. They have some tables, they have some relations, and they have some graphs. And being able to work with both of them uniformly is an important strength. And so I think this emergence of graph-specific systems, while it does suggest that there's performance issues sometimes with modeling these traditionally as relations, and that's one thing we'll talk about in a couple of segments, it's not clear to me that capturing the entire world as a big flat graph is necessarily the right thing to do. It seems like you want a model that can do both, relations and graphs, and sort of interchange between them. Okay. Make one more point about Sparkle before we move on to some more complicated examples. So summarizing what we sort of said, while Sparkle is designed for graph query, there's a few problems that I want to point out. One is this notion of algebraic closure that we brought up when we talked about relational algebra. So the input is a graph to Sparkle. You can query a graph, but the output, if you go back to the slide on Sparkle and you look at the result, it's actually a list of records. It's no longer a graph. It doesn't have to be these triples anymore. And so therefore, I can't take the result of one Sparkle query and then again query it with Sparkle. The only thing I can query with Sparkle is a graph. And so one way to say this that maybe is a little bit pedantic but is more technically correct is it's not algebraically closed. It returns a different type of thing than it takes as input. But this is a big disadvantage as we've seen, right? You want to be able to chain queries together whenever possible. This is what gives you a foundation for features like logical data independence, which we argued back in the relational lectures as a really critical feature. Okay. Second, I'd argue that there's actually limited expressiveness, and we'll see some examples of this in a little bit, but you can't do these graph traversal tasks that we talked about. Most of these you can't express in Sparkle. Since version 1.1 in Sparkle, there is support for these path expressions that can express some forms of traversal, but it's not clear that all the general recursion is supported. Right. And you need general recursion, you need general graph, in order to implement these graph traversal tasks, you need some way of sort of walking over the entire graph as a whole, and Sparkle doesn't necessarily provide that. Okay. And then as we just pointed out in the last slide, if your input starts off as tables, before you can even touch it, you have to shred it into triples and model the whole world as a big pile of graph edges. While what's nice about graphs is you can actually do that. There's always a way to sort of shred it into a graph in some form. But the process of doing that might blow it up by a factor of 3 or a factor of 6 is what we see in practice, depending on exactly how you model things, depending on what your table structures look like. But this is, a tough hill to climb, to try to recover that performance that you give up just by shredding it into a graph. So again, I think what this tells me is that we want a system that can handle both graphs, can express graph traversal tasks, which SQL is not great at, and we'll talk about that in a moment, but neither is Sparkle, but can also work with tables in whatever form they're in. Okay.